Okay, we are now recording. All right, so my goal is to finish 2.6 today, and then at the end of class, give you a quiz on the epsilon and delta proof, prove a limit using epsilon delta from section 2.4. Okay, now I'm going to try to finish 2.6, but in case I don't, I'm going to be jumping around with the problems. So you might see me bouncing back and forth. If that's the case, I apologize, but I want to make sure I show you at least one of each different type of problem. So in case I don't finish, if I do kind of keep it in order, right? And then there's some problems that I didn't get a chance to cover. Okay, so my goal is to show you at least one of each type. And then if there's time, I'll jump back to another of that type. So I'll be kind of going out of order. But I'm hoping to do a 2.6. 2.7, 2.8, all of next week is on the derivative. And I gave you the section on the derivative, just one formula for the derivative that I gave you on that page yesterday. So check that out. That's over there, okay? So I will go and do stuff there, and it might be a little bit out of order, but that's the way it's going to be. So I can make sure I show you at least one of each different type of problem. Okay, so 37, 2.6, 33 first. Sorry, 33. Limit as x approaches negative infinity of x squared plus 2x to the 7th. Now you can't plug in this directly because if you plug in a super big negative, that's going to be positive, that's going to be negative. So what happens when you have a big number minus a big number? You can't tell right away. Okay, but instead you can do some factoring. Okay, so if you factor out right away, then it makes it a little bit easier. Okay, so factor out the x squared times 1 plus 2x to the 5th. Now you can kind of tell what happens. Okay, if you're plugging in a super big negative, right? This is a large positive. This will be a large negative. Negative a million. Cube it, it's negative. Times 2 is negative. And then if you add 1, is insignificant. It's basically a large negative. Okay, so what happens when you have a large positive times a large negative? You get a large negative. So the answer is negative infinity for 33. Okay. Okay, 35. Limit as x approaches infinity of arctan of e to the x. Okay, if I plug in a super big number, e to the x is big. I plug in a million. E to the million is huge. So I'm taking arctan of a super big number, and we saw that yesterday. Okay, that comes out to be pi over 2. Okay, so here's the graph of arctangent again. So you have horizontal asymptotes at pi over y equals pi over 2 and y equals negative pi over 2. Okay, so inverse tangent of a super big number is pi over 2. Make sure you're in radians. Inverse tangent of negative big number is negative pi over 2. So this one's going to be pi over 2. Okay, so that is that. Okay, then let's see, I'm jumping back to problem 21. And the only thing about 21 was you just had to multiply it out. So 21, limit as x approaches infinity, 2x squared plus 1 squared over x minus 1 squared, x squared plus x. Okay, so we are going to multiply it out, but just to get a feel of this a little bit. Okay, thinking ahead, if I multiply this out, this is going to be 4th degree, right? It's going to be 4x to the 4th plus some other stuff. Okay, and how about the bottom? The bottom is also going to be x to the 4th and some other stuff. Okay, so it's basically 4x to the 4th divided by something with x to the 4th. Okay, so anyway, at first I multiplied it all out. So I squared this, 4x to the 4th plus 4x squared plus 1. X minus 1 squared is x squared minus 2x plus 1. And then I multiply that by x squared plus x. Okay, so 2x squared plus 1 squared is 4x to the 4th plus 4x squared plus 1. That's squaring a binomial. X minus 1 squared is that. Okay, now you can multiply this bottom out. So you go x squared times each of these, and then negative 2x times each of these, and then 1 times each of these. Okay, and this is what it looks like. So x squared times x squared is x to the 4th. X squared times x is x cubed. Negative 2x times x squared is negative 2x cubed. Negative 2x times x is negative 2x squared. And 1, well, when you multiply by 1, you just copy these, right? X squared plus x. Okay, so I've got 4x to the fourth plus 4x squared plus 1 on top. The bottom, combined like terms, x to the fourth. These two give me a negative x cubed. These two, negative x squared plus x. Okay, so I have 4x to the fourth plus blah, blah, blah over x to the fourth plus or minus blah, blah, blah. Okay, so they're both fourth degree. So once I finally multiplied all this mess out, I divide top and bottom by x to the fourth. That was that trick. And that pretty much does it. And the key is this will give me a 4. This will give me a 1. Everything else is going to have an x in a denominator. Okay. So watch, if I divide 4x to the fourth divided by x to the fourth is 4, right? 4x squared divided by x to the fourth is 4 over x squared. And that's 1 over x to the fourth. Okay, and then bottom, x to the fourth over x to the fourth is 1. That divided by that is minus 1 over x. That divided by that, minus 1 over x squared. X over x to the fourth is 1 over x cubed. Okay, and again, when you're doing this for me, keep writing limit, lim, x approaches infinity until you're quote unquote plugging in. Okay, now if you plug in a super big number, that's what that means, like a billion, that one, that one, that one, that one, and that one all approach 0, right? If you divide by a super big number, you end up with a super small number. So it's essentially 4 plus nothing over 1 minus nothing plus nothing, or 4 over 1, which is 4. So the answer is going to be 4. Okay, so that's it on a deeper understanding scale. For real big numbers, this is basically 4x to the fourth divided by x to the fourth. Everything else behind it drops into insignificance, right? X cubed, x squared, x and constants, they all lag way behind raising something to the fourth power. Okay, so in the limit, in the long run, you're basically just saying 4x to the fourth divided by x to the fourth, which is 4. Okay, now you can't use that as a proof. You're not allowed to use that as a proof, but that's just, you know, the idea behind that. Okay. Okay, then I want to jump ahead to one of the graphs at the end. A quick graph, 2.6, 61, and 63. So here's 61. And let's see what time it is. Okay, quick graph of y equals x to the fourth minus x to the sixth. We can actually get more specific later, but right now we're not going to. Okay, so a quick graph of this. So first I factor out the common factor of x to the fourth, 1 minus x squared. And we know 1 minus x squared is 1 plus x, 1 minus x. So x to the fourth, 1 plus x, 1 minus x. Okay, first thing I notice about this function is that it's an even function, right? If I replace x by negative x, I get the same thing, which tells me I have symmetry with respect to the y-axis. Okay, so I'm going to have y-axis symmetry. Okay, so the first thing I do is lay down the zeros. Pretend you didn't see the whole graph, but the zeros are 0 plus or minus 1. Okay, so yeah, now it's kind of corrupted because you already see the answer. But right now, put -1, 0, and 1. So I have just those 3 dots. And my paper's crooked on top of that. Okay, so does the graph go above or below? All you got to do is just pick a number in between. Okay, so pick a number between 0 and 1 and a number after 1. Okay, so ignore this. I already know the function's even, so I'll just work on this side and do the mirror image. Okay, so let me plug in, say, a half. Okay, now, x to the fourth is always positive as long as I don't plug in 0, right? So the sign is completely determined by 1 minus x squared. Plug into that. Okay, so if I plug in 0.5 or a half, 1 minus 0.5 squared, that's positive. That tells me it goes up. Plug in a number like 2, 1 minus 2 squared, negative. Therefore, it goes down. Okay. All right, so we played that game before. Plug in a number here. Is it positive or negative? it's positive, so it goes up. Over here, it's negative, so it goes down. And since I know it's an even function, I just do my mirror image, reflect across the y-axis, and there's my graph. Okay. And if you want to say what this says x approaches either plus or minus infinity, y approaches negative infinity. Okay. Plug in a super big positive or negative, you can tell by the square. This is always positive. But if I plug in, say, either a million or negative a million, this quantity right here is going to be negative. So positive times a negative is negative. So it shoots down like so. Okay, so for a quick graph, lay down the zeros and just determine, does the graph go up or does it go down? Now, I put these points right over here, assuming this is the maximum, but I don't know this is the maximum point. Okay, I just know it goes up here. It may go up like this and then come down here somewhere. Okay. Once we go to the next chapters, develop the calculus, we'll be able to find these maximum points or minimum points. Okay, one of the powerful tools of calculus. Okay. All right, so let's see, as long as I did that, let me go ahead with the other graph. So I think I've shown you at least one of each fundamental type of problem. Time is at 9:25-ish. Okay, so the next one I want to show you was 63. Y equals 3 minus x, 1 plus x squared, 1 minus x to the 4th power. Okay, so get the zeros. The zeros are 3, -1, and 1. Raise it up there. Okay, so what makes this 0? 3, -1, and 1. Okay, so as you're doing this problem, again, I've already shown you the answer, but pretend you don't see that. There are the zeros, right? -1, 1, and 3. So now I just pick a number in between and see, does it go up or does it go down? This function doesn't have any symmetry, so I can't do that. But one thing you will notice when quote unquote plugging in, that's always positive. That's always positive, right? 1 plus x squared and 1 minus x to the 4th are always non-negative. They're positive or maybe 0. Okay, so when I plug in numbers, I can ignore these two guys because they're already positive. Okay, so pick something over here like -2. Okay, 3 minus a -2, positive. These are already positive, goes up. Okay. 0. Don't even look at these. They're already positive. 3 minus 0, positive, goes up. In other words, f of 0 is greater than 0. About here, 2. 3 minus 2, positive. That's already positive. So again, it goes up. F of 2 is greater than 0. Finally, when I plug in a number like 4, I get negative, right? 3 minus 4 is negative. I already know these are positive, so that goes down. Okay, so what do I have here? As x goes to infinity, y goes to negative infinity. Okay, we knew that already here, but if I plug in a super big number like a million, 3 minus a million, negative. These are already positive. Goes down there. This says x approaches negative infinity, y approaches infinity. Plug in negative a million, 3 minus a negative a million, 3 plus a million, that's positive. We already know these are positive. So that goes up here. And then I plug a number in between, like 0 and 2. So that gave me that. Okay, so that's that one. Okay, then we had some problems asking for asymptotes, 47 and like 51. Okay, y equals 5 plus 4x divided by x plus 3. Find the vertical and horizontal asymptotes. Okay, VA stands for vertical asymptote, HA horizontal asymptote. Okay, vertical asymptote, horizontal asymptote. I think we've seen that before. Okay, vertical asymptote, just set the denominator equal to 0. X equals -3. Okay, does that always work? No. The next problem, it doesn't quite work that way, and I'll show you why. Horizontal asymptote, let x go to either infinity or negative infinity. So this is first degree. This is first degree. Play the trick of dividing top and bottom by x. So 5 plus 4x divided by x. x plus 3 over x. Let me raise it up so you can see that a little bit better. Okay, then I divide. That's 5 divided by x is 5 divided by x. Plus 4, right? 4x over x. Divided by x over x, which is 1, plus 3 over x. Okay, and now if you plug in a super big number, either positive or negative, plug in 1 billion, that's like nothing. That's like nothing. So it's 0 plus 4 over 1 plus 0, which is 4. And even if I plug in negative 1 billion, 5 divided by negative 1 billion is still nothing. Likewise, 3 divided by negative 1 billion is still nothing. So you get the same limit. Okay, so my horizontal asymptote, y equals 4. Vertical asymptote, x equals negative 3. Okay, 51's a little bit trickier. Okay, so first factor. So the top is x times x squared minus 1, which factors into x times x plus 1, x minus 1. Okay, the bottom factors into x minus 5, x minus 1. Okay, so factor, factor, factor. Okay, so at first glance, you might say, okay, x equals 5 and x equals 1 are vertical asymptotes, but not this time because you get a cancellation. See how these two cancel out? That basically gives you a hole. You have a removable discontinuity. Okay, so I cross this out. I have x times x plus 1 divided by x minus 5, where x is not equal to 1. Okay, so the only vertical asymptote is x equals 5. Okay, is there a horizontal asymptote? The answer is no, because now this is second degree, right? X squared plus x, second degree, first degree. So for super big X, the top's going to win. We do not approach any one number. Okay, the expression is going to go to infinity. So that tells me there's no horizontal asymptote in this particular case. Or even at the get-go, right from the start, right? X cubed is going to beat x squared. So in the long run, it behaves like y equals x. Okay, in the long run, you ignore anything behind it. That drops into insignificance. So does that. So does that. So you just look at x cubed divided by x squared, which is x. So that does not approach any one number. Okay. All right, and that is that one. The only last one I'm going to talk about involves something called the squeeze theorem. That was 65. So I alluded to it briefly before, but we'll need that for problem 65. Okay, so back on page 101, 2.3, the squeeze theorem. Okay, if f of x is less than or equal to g of x, less than or equal to h of x, where x is near a, except possibly at a, limit as x approaches a of f of x equals the limit of x approaches a of h of x is L, then limit as x approaches a of g of x equals L. Okay, it's probably best understood by the picture. Okay, you have three functions, f, g, and h. F is the lowest, g is in between, h is the top. Okay, the two extreme ones, the highest and the lowest, both approach the same limit L. G is squeezed between the two, so therefore it also has to approach the same limit. It's called the squeeze theorem. Okay, sometimes it's called the sandwich theorem. Okay, the top and the bottom. Okay, then anything in between has to go to the same limit. Okay, so the lowest function approaches L, the highest function approaches L, so anything that's squeezed between them has to approach the same limit. Okay, so how do I do that for problem 65? And then I think that's about it after this one. So for 65, we're asked to show that the limit as x approaches infinity of sine x over x is 0. Okay, so here's the way that one works. We know from trig, -1 is less than or equal to sine x less than or equal to 1, right? Okay, divide them all by x. The inequality symbol stays the same if x is positive, and it is. X is approaching infinity. So I have -1 over x less than or equal to sine x over x less than or equal to 1 over x. Okay. So smallest, largest, in between. Okay, what happens to the smallest? Limit as x approaches infinity of -1 over x. Negative 1 over a million, negative 1 over a billion, negative 1 over a trillion, 0. How about the largest? Limit as x approaches infinity of positive 1 over x. 1 over a million, 1 over a billion, 1 over a trillion. That also approaches 0. This function is squeezed between the two. So therefore, by the squeeze theorem, the limit as x approaches infinity of sine x over x also has to be 0. So that's an example of how the squeeze theorem works. Frankly, there aren't that many problems involving the squeeze theorem. So I guess as far as Homer problems are concerned, it's kind of a minor theorem, but it's there nonetheless. Okay, so the two extreme functions both approach 0. So anything stuck between them also approaches 0. Okay, so the problem's done, but I'll just show you a little bit about what the graph might look like. Then I think I'm just about done. Okay, we know that 1 over x looks like this for positive x. Negative 1 over x looks like this. Okay, sine x over x, there's a trig component to it. It's going to bounce back and forth, but it stays between the two, right? It squiggles, because of the sine, it touches the x-axis quite a bit. Okay, so when x goes to infinity, the bottom graph approaches 0, the top graph approaches 0, so therefore sine x over x also has to approach 0. Okay. All right, I think that's all I was going to share with you. Let me take a quick look at my notes. Okay, I'll just mention again, definition of the derivative, okay, that I showed you last time. Put this on your cheat sheet if you wish. So next week we'll be doing quite a bit of this. Okay, the definition of a derivative. Okay, this is the only one to use. Now the book has quite a few in sections 2.7 and 2.8, but that's the only one you need to concern yourself with. Okay, the derivative of f of x is f prime of x. Okay, so the way we say it is f prime of x. And there it is, limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's what you're going to be using. Don't use any of the other definitions, although they're correct. What Mr. Stewart has is correct, but you don't really need them. Okay, you can survive with just this. Okay, all right, so I think I'm done. So on my schedule, I can knock off 2.6. So next week we'll be doing derivatives, and more derivatives, 2.7 and 2.8. Okay, and again, we're aiming for the test a week from today on the 26th, right? Okay, that'll do it, folks. So get your cell phones out for taking a picture. And here is the quiz. I'll raise it up. Okay, use the epsilon and delta notation to prove the following. Limit as x approaches 3 of 2x equals 6. It's very believable, obviously, but prove it using techniques of section 4. So always start off using the same language, right? Okay, given epsilon greater than 0, find delta greater than 0 such that, right? And then it says 0 is less than absolute value of x minus a is less than delta. Arrow implies absolute value of f of x minus L is less than epsilon. Okay, so first identify what's the A. You should be able to tell from there. What's the f of x and what's the L? I kind of already gave you the answer because I'm just going left to right, right? So there isn't much choice. Okay, so there's two parts to it, right? The first is the derivation, finding out what delta is in relation to epsilon, and then going through the actual proof. Okay, if you're not sure what to do, look back at stuff we did in section 4. Okay, give you just a few more seconds to either write it down, take a picture, do a screenshot, or whatever you need to do. And then go ahead and get started, and then it'll take me a minute to set your breakout rooms. Okay. Again, limit as x approaches 3 of 2x equals 6. All right, I will now assume that you all have it. So go ahead and get started. Okay, I will pause. I will turn off the recording. We don't need to record.